In this video, I am going to cover the scenario of masses suspended by a frictionless pulley. So as the question says, we have two masses denoted by small m and capital M. They are suspended by a pulley and the masses are moving as per the direction shown, which is clockwise for the string or the rope on the pulley. And we have to find the acceleration a with which the mass m, small m and capital M are moving along with the string. And then we have to find the tension T in the string. And then for the special cases, as given in question C, find the values of A and T applicable. And finally, we have to find the net force, F net, on the big M and the small m. And what is given is that the string is massless and inextensible, and the pulley is massless and frictionless. Now, to be able to derive the expression for A and T, we need to consider the free body diagram, which in this case is applicable for objects 1 and 2. So let's first consider object 2. About the gravitational force between object 2 and Earth, the two forces involved are the force by Earth on object 2, which is given as the weight of the object, m times g. And the other force out of the action-reaction pair will be force exerted by object 2 on Earth, F2E. And together, I have indicated them with a dedicated color, and they represent the action and reaction pair. Also, another pair is shown in the red. So the first force in that is the force by the string or the rope on object 2, and then the force by object 2 on the string S or the rope. So they also together make a action-reaction pair. Out of the four forces just described, it's important to see what are the forces that are acting on the object 2, which is under consideration. So first force that is applicable for object 2 is Fe2, and the second force applicable for the object 2, which is acting on the object 2, is Fs2. So now let's consider what are the forces applicable for object 1. So this time, if we focus only on object 1 and try to understand what are the forces applicable, then the forces are force by Earth on object 1, which is given as the weight of the object, which is m times g. And then we have the other force in the action-reaction pair, which is force by object 1 on Earth, E. So that makes one pair of the action-reaction force. And then let's see the second pair. That's force by the object 1 on the string or the rope, and which is equal and opposite to the force by the string or the rope on object 1. So overall, there are two pairs of forces acting on object 1. And let's see what are the forces which are acting on the object 1. As I have indicated with a dot, this is Fs1 is the force applicable acting on the object 1. And then we have Fe1, which is again acting on the object 1. Now, if we focus specifically the forces acting on the object 1 and 2, then the free body diagram respectively looks like this. So for the object 2, in the downward direction, we will have the weight or force of mg, which will be higher than the upward force acting on it, which is represented by tension T, which is actually the force S2. And since mg is greater than T equal to Fs2, so overall the object is moving in the downward direction. And since the force mg is greater than the force tension or Fs2, the motion of the object 2 is in the downward direction. Now let's focus on the object 1. Here we have again the two forces acting on the object. First is the tension T, which is same as Fs1 acting in the upward direction, and the weight Wmg in the downward direction. Now, in this case, since the object is moving in the upward direction, so therefore the tension should be greater than mg. Now, it's important to understand before we proceed any further about the speed of the masses when they are in motion. So let's say at time t equal to 0, when the two objects are at rest, they are at a certain height with respect to the ground or the pulley. As soon as the two objects are set in motion, after a duration of time t equals to t, when they are in motion, the object 2 would have traveled a distance of h in a time t, and therefore its speed will be given by the expression h over t. And since it is given that the string is inextensible, it means the length of the string cannot increase with the application of the weight, and therefore the length is constant. So if object 2 has moved down a distance of h units, then the object 1 will have to move up by the same distance, height h, vertically up. So it is important to understand that the speed of the two objects will be the same, while the velocity of the bigger object will be pointing vertically downwards. The velocity of the smaller object will be pointing opposite, that means vertically upwards. Now, how about the acceleration of the two masses? So we know that the speed at any point of time, at any instant of time, is the same for the two masses. So we can safely write u2 equals to u1, and therefore at any given point of time t duration later, uh, the speed will also be v2 equals to v1. Now, using the equation v equals to u plus at, and for a given time t, we know that a therefore has to be same. Yeah. So therefore, the two masses move with the same acceleration, but of course, the direction is opposite. So let's first derive the expression for the acceleration a of the masses and the string. So if we focus on the free body diagram for the bigger mass, the direction of motion of the bigger object is given going vertically downwards, which is, we take it as a positive direction. So here I mentioned the sign convention for convenience. So the downward direction, I take it as positive, which is the same as the direction of motion, and the opposite direction will be with a negative sign. So focusing on the free body diagram for bigger mass, we have mg, that is the weight, minus t, tension acting vertically upward, will be equal to the mass times the acceleration of the object. Similarly, for the smaller object, since it is moving up, therefore the tension vertically acting upward will be higher than the weight of the object. So T minus mg will be equal to the mass times acceleration of the object. And in the previous slide, we have seen that the acceleration of both the objects has to be a. So now we have two equations, 1 and 2. Simply add them. So we get this, which means we arrive at this, and which means the expression for a is m minus m over m plus m times g. And just to be sure that the units of the acceleration we have derived are correct, so in the numerator we have the mass, and then denominator has mass. The units cancel. then the value or the units of A is the same as the unit of G, which is the verification. So having found the value of A, it should be very easy to now find the tension T in the string using the two equations from the free body diagram that we have. So we have equation 1 and 2, and then in the previous slide, we derived an expression for the A. Now, if we put the value of A into any of the two equations, so let's say we put it in equation 1, then this is the path. You can go through the calculations I have shown. They're pretty easy to understand. And then if I take option 2, that means equation number 2, the set of equation and the derivation will look like this. So as you see, both of them will yield the same result. And it's important to analyze that the expression for T will be equal to the product of the masses twice that, and in the denominator we have the sum of the masses. So 2mm over m plus m times g. Now also important to verify the unit of T. We know that tension is a force, and therefore it should have the units of force. So in the numerator we have mass times mass, and in the denominator we have only mass. So this will result into the units of mass times the units of g, which is nothing but Newton. So with this, we know that our derivation has the correct units representing a force. Now, coming to specifically about the tension T magnitude and direction, it's very important to understand that the tension T has to be the same in magnitude on both the sides. Now, it doesn't matter whether the string or the system is at rest or the string is moving with certain acceleration. T has to be same, equal and opposite in terms of direction. So now let's see the values of A and T for the special cases mentioned in the question. So bear in mind that A is equal to m minus m over m plus m times g, and tension is 2mn over m plus m times g. So for the first special case, when the two masses are equal, so obviously the difference of the two masses will be equal to 0, and therefore the acceleration will be 0. And applying for t, this will be twice m times m over m plus m, and the denominator will become 2m, and 2m on the top will cancel with 2m in the bottom, and therefore it will become mg, which will be equal to. So what this essentially means is that we have the pulley with the equal masses m and m on both the sides. So if we see on the right hand side, the weight mg cancels with the tension mg in the upward direction, and on the left hand side also the weight mg cancels with the upward force or tension mg. So as a result, the string and the masses are at rest. Now let's see what happens for the case 2, where the bigger mass is twice the smaller mass. So if we put in the values in the formula, we get for acceleration 2m minus m over 2m plus m times g, so which is equal to m over 3m times g, and this m and m in the numerator and denominator will cancel, and which will be equal to g over 3. So that's A. And then about T, the tension in the string on both the sides will be equal to twice m times twice m over twice m plus m times g. So which in turn will be 4 times m times m over 3m times g. So this m and m will cancel, which is 4 over 3 times mg. Now, if you see this case with respect to how it looks like pictorially, so we have the bigger mass 2m. For the free body diagram, the downward force will be 2 mg and the upward force tension will be 4 over 3 mg. And for the smaller mass, respectively, the forces will be mg in the downward direction and 4 over 3 mg in the upward direction. So if you do a simple calculation, for example, what is the net force on the 2m object? That will be the downward force 2 mg minus 4 over 3 mg. That is the upward force. That will be 2 mg over 3. And if we have to find out the acceleration for that mass, it will be F net divided by 2m, which is the mass, which will give, as per this calculation, g over 3, which matches also with the earlier value of acceleration we derived. And then we should also be able to cross-verify the F net, the net force on the smaller mass m, which will be 4 mg over 3. That's the upward tension force minus mg, the weight of the object in the downward direction. That will be equal to mg over 3. And then if we have to find the acceleration of m, that will be the net force over m, which is mg over 3m, which is g over 3, which is again matching with the acceleration that we derived earlier. Now, purely for academic interest, I calculated the values of a and t for other special cases. Let's say, for example, the bigger mass is n times the smaller mass, and definitely n is greater than 1 in that case. So if we substitute the values, I'm sure you will be able to do the calculations on your own. You should be able to get a will be equal to n minus 1 over n plus 1 times g. So if you look at this number, the number n minus 1 will always be lower than the denominator n plus 1. And for that reason, acceleration in such a system will always be less than the value of g. Now, similarly, if we apply it for t, we get 2n, which is can be written as n plus n over n plus 1 times mg. Yeah. So obviously n plus n will be a number which will always be greater than n plus 1, and therefore tension will always be higher than the weight of the smaller object. So these are very minor observations that should be kept in mind. Need not remember by heart, but it's very important to understand how the values change. Now let's take the next case. Now, if we take the next case that m is very, very high as compared to m, then we apply the same logic. So n minus 1 will always be lower than n plus 1, and therefore a, as we have seen, will be less than g. But what is the limiting value, I would say? So as n approaches to a very high number, n minus 1 can be written as roughly equal to n. And n plus 1 can also be roughly written as n. So these two cancel. So the value of acceleration, it will approach the value of acceleration due to gravity. It will never be equal to g, but it will always approach. Yeah, the limiting value of a will be g. Now let's apply the same logic over here. So for tension, 2n, when n is a very high number, can be written as 2n, but the denominator can be written closely as n plus 1 will be roughly n. So in that case, this will cancel, and therefore tension value will be twice mg. Yeah, so the limiting value of tension, it will never be equal to twice mg, but it will approach that value. And given the condition that m is very, very less than m, so therefore twice m will also be very, very less than m, and therefore tension will always be less than the weight of the bigger object. Now let's take the final case where either of the masses is 0. So either m equal to 0 or m equal to 0, or let's say we produce a situation where we cut the string. So in those cases, therefore, in those cases, the objects will fall freely under the influence of gravity, and a equals to g. And then, of course, when there are no masses connected to the strings, so tension will be 0. It is as good as the two objects falling purely under the influence of gravity. Now let's see the net force on both the masses. So net force on m, so that will be the mass of the object times the acceleration. And what's the net force on the other mass? That is given by the mass of the object times acceleration. Now, note very important that we have seen earlier that acceleration has to be same on both the sides. Yeah, so that's very important. And then substitute simply the values of a. So that will be force on the bigger object will be its mass times the value of the acceleration, which we have derived earlier. Similarly, the net force on the smaller mass will be m times a, substitute the value for a we derived earlier. Now it's also very important to see that the net force on the bigger mass has to be higher than the net force on the smaller mass. And what's the ratio of them? It will be in the ratio of the masses of the objects respectively. Let's try to understand a very interesting alternative approach to understand the scenario and come to the expression for A. So let's say we have a system indicated by the boundaries of this box. And when I say the system, it has the components, the smaller mass, the bigger mass, and also, of course, there is a rope. Yeah. So we can assume that the objects are on a surface which is frictionless. Yeah. And with this, we now apply the forces that are equivalent of the forces that were acting in the case of a system of pulley. So on the right hand, you see there is a force m times g being, which is actually the weight of the object, which is trying to pull this system on the right hand side. And of course, the other external force we are talking about is the small m times g, which is a force acting on the smaller object, which is trying to pull the system towards the left hand side. So we can simplify this with the second picture as follows. For the same system under consideration, we can arrive at the net external force, which is m minus m times g, and that's a force acting, trying to pull the object. Yeah, so we draw the only net force, which is resultant of the two forces, and therefore the simplified picture looks like the second picture. And we have to ultimately and eventually the third picture presents the view of the system in such a way that the rope or the forces acting due to the rope or on the rope are ignored because they are not they do not they are not visible to the outside world. Yeah, so from the outside world perspective, there is a net force which is m minus m times g, which is trying to pull this system, which is made up of the masses m and m. And of course, we are given that the string or the rope doesn't have any mass. So with respect to what we have seen so far, F net can be written as m minus m times g, and therefore the acceleration we know that is given by F net over the total mass of the system. And what's the total mass? So acceleration will be m minus m times g divided by the total mass, which is m plus m. Yeah. And then, of course, having found out A, we can use any of the two free body diagram equations, which we have seen earlier, mg minus t equal to ma and t minus mg equal to ma. So although we saw these equations in the free body diagram, but they can also be seen with respect to the free body diagram here. So referring to the first figure for equation, we have a force mg, which is pulling it towards the right, minus the force of tension, which is pulling it towards the left, and that will be equal to the mass of the object, m, times the acceleration with which the object is moving towards the right hand side. And for the free body diagram, for the smaller object, since it is moving towards the right, so that will be force of tension minus the force which is pulling it towards the left, mg, will be equal to mass of the object times the acceleration with which the object is moving towards the right. So we see that the equations are free body diagram equations are valid in both the scenarios, and eventually the value of tension T will be equal to 2 mm over m plus m times g. Now talking about the displacement, velocity, and acceleration for the masses, and also the string on the left hand side and the right hand side. As I mentioned earlier, the height which is traveled, or the distance which is traveled by the right hand side of the string while going in the downward direction, if it is h, then since string is inextensible, this implies that the small mass m, or the left hand side of the string, will go in the upward direction by the same height h. And therefore, with respect to the displacement, the magnitudes of the displacement on both the side, which is nothing but the distance h, they are equal. However, as we understand from the picture, the directions will be opposite to each other. Now, talking about the velocity, since velocity is given by, or I would say first the magnitude of velocity, which is the speed, since the speed is given by distance over time, which in this case is h over t, and h is same for both left hand side and right hand side, and the time is also same for both the sides. The event is happening in the same time, left side going up and right side going down in the same time. Therefore, the speed v2 will be equal to h over t, and speed v1 will also be equal to h over t, and therefore we conclude that the speed on both the sides will be same or equal. From velocity perspective, the magnitudes of the velocity, which is speed, it's equal on both the sides, and then of course the direction is opposite. And now talking about the acceleration, we know that the acceleration is defined as the rate of change of velocity. So a2 will be given by v2 minus u2, let's say final velocity minus initial velocity, over the difference of the time it happens. And similarly, for a1, it will be v1 minus u1 over the duration of the time it happens. And we know that v2 is equal to v1 because speed at any time for the two sides is the same. And also u2 has to be same as u1 for the same reason. Therefore, the numerator for both the sides and also the denominator for both the sides is same. And therefore, we conclude that acceleration a2 equal to a1 equal to a. So to summarize, the magnitudes of the displacement, velocity, and acceleration are equal for the mass small m and capital M. And also the directions for all the three physical quantities are opposite to each other.